Hi, so we'll talk about the linked list class in the general linked list implementation. So we have a node class, it holds no data, but we'll use it to build a linked list with a chain of these nodes. And in this linked list class, it's going to manage the structure of the eventual linked list that will hold data. Okay, and as anything would have to do with the linked list, the most important node is the first node, right? Given the first node, we can get to the rest of the nodes and the data. So in a stack, we call the first node top. So in a general linked list, probably doesn't make a whole lot of sense to call it top. It's typically called the head. So the first node, head. Now, so in the dunder init method, we are going to create a self.head, and we are going to set it to a new node, which, depending on your experience with linked list, may or may not be the typical thing to do. And what I mean by that is this, that remember in our stack implementation using linked list, we in the dunder init method, we actually set the top attribute to none. Okay, so an empty list in that, or an empty stack in that case, is when the top is none. Here we are doing something different, that this, we're taking this header node approach, that the head node will always exist, even for an empty list. However, it will be different from the rest of the nodes in that it will never hold data. So even though there is a node here, this uh, uh, linked list initially is still considered empty. Okay. Now, the reason we're doing this approach is, well, I mean, there are different approaches to implementing linked list, like I said before, and this approach is nice in the way that we can treat the head kind of just the same as any other node, because in the in the in the other approach, the head could be none or it may not be none, right? However, in this approach, head is always pointing to a node. So in that case, we don't have to have a special check on if head is none. But we still have to be careful because this head node, again, it does not hold data and it's supposed to be, internal and invisible to the outside world. So let's see how this header node actually changes things. And to do that, we'll return to our familiar stack behavior, because as we've seen before, we can, or linked list can be used as a stack with the right operation. So stack supports push. That's the first operation we implemented. And we're not going to call it push here. We're just going to call that operation add to head. So and add to head basically takes a new node, and this new node should have data, well, at least in the eventual linked list that will hold data. Yeah, because remember, the only node that doesn't hold data is the head node. Anyway, so it's gonna take this new node and make it the first node in the linked list, or the first node as far as the client or outside world is concerned. Now remember, internally though, the head is always the first node in the whole linked list. So what can we do to um, implement this add to head? Well, we can simply put this after the head node by calling head.insert after and give it a new node. And this is the resulting picture. And as far as the head node is concerned, nothing changed there. It's still what it was before, but now the new node is the first node after the head node. So this is the push operation. What about this pop operation? Well, we're not going to call it pop here. We're going to call it remove from head. And what it will do is, well, it won't change anything. It won't change what the head points to because this header node is always there. But it will remove and return the first node that holds data after the head node. Well, what can we do? Well, remember in the node class, we implemented a remove after method. So that will do exactly what we want. So we just have to call that method by dereferencing the self.headNode. And, and that will remove the node right after the head node, and it'll return it. And here's the question. What would this method do, or what it returns, if the linked list is empty? And you will likely need to look into the implementation of node remove after to see what happens there. All right, so here is the code. This is the node remove after. Now, if the linked list is empty, head does point to a node, but the head's next pointer is none. So temp basically will be assigned to none here, and if none, that will be false, so it won't do anything. It will simply return none here. So that means if the linked list is empty, remove from head will return none. Okay, so that is just for this our particular implementation. I should remember in our stack implementation, if the linked list is empty and we try to pop, it actually raises an exception. So that kind of depends on the in the particular implementation and what the requirements might be. And here is another question, and that is how do we write a method to check if the linked list is empty? So pause the video and give that a try, please. So from our linked list based stack implementation, the is empty checks if the top is none. Now in our case, where we know the head is always there, then we don't check if the head is none, but if the linked list is empty, that means the head dot next is pointing to nothing. So the linked list is empty if head dot next is none. So that's the if empty method. So now let's try to write the dunder string method. And remember the purpose for the dunder string method, at least for the linked list that will eventually hold all the data, is that it will show all the data that's in the linked list. So that means it should show every node except the head node, because excuse me, it doesn't contain any data. So the way we'll write the dunder string method is very similar to the one we wrote before for the linked list based stack, that we're going to have a pointer that points to each of the nodes in the linked list in turn. And we're going to start with the head, right? Just like before. However, the difference here is that when we start from the head, we don't really check if temp or the head is not none, because we know it's not none, right? Because the head is always there. So rather than saying while temp, we'll say while temp.next. So it's going to start with the first node that holds the data. So here you can think of kind of the temp.next, then it's really kind of the current node. And we're going to move the temp node by the next pointer each iteration of the loop, and we are just going to add each the string representation of each node to the string that will accumulate all these nodes together. Right, so let's actually see how it works by stepping through an example here. So here the linked list just has two nodes that will eventually hold data. Okay, so we're going to start with temp pointing to the head. So that's that. And when we do this check, temp.next, that's true. So we come in here, temp has been moved to the temp.next. So it's already pointing to the first node that actually will hold data, and it's going to add that data or whatever the string representation for that node is to the return string. So uh, in this case, so we just have the ID for now. And then it's going to come back to say, okay, temp.next. Well, temp.next is still pointing to something, so it's true. Then we'll come in here, we advance the temp pointer, and then the string representation of this node is going to be added to the return string. And we go back to the condition of the loop, temp.next now is pointing to none. We've reached the end of the list. So this is false, and this return string is what's going to be returned from the string method. Now I've already typed the code out here. It's slightly more complicated, but it's really just to make things look a little nicer. But the idea is exactly the same. And I have a little demo here that initializes an empty linked list and add to head 3 nodes. And let's run this and see what we see is basically we have 3 IDs because there are 3 nodes. So that's the string representation of a linked list without data.